Okay, so the last paper for this session will be presented by Daniele Cono Delia, and he's a tenure-track assistant professor at Sapienza, University of Rome, and his research spans different fields in software and system security, in general investigating how program analysis techniques can be used to improve the accuracy and performance of security policies. And today he will present the paper Predictive Context-Sensitive Fuzzing.
Thank you, Antonio, for the kind introduction. So I'm Daniele Conodelia. I work at Sapienza University of Rome, and this is a joint work with other folks from Sapienza, from Eurecom, and from Vrije Universiteit Amsterdam. So I want to talk about coverage-guided fuzzing. We know that this is a very popular and successful flavor of fuzzing, where when you generate a test case, what you do is normally you instrument your program to collect some feedback, some coverage feedback on how this test case exercises different parts of the program. The moment that you determine some novelty, some facts, some coverage information that you haven't seen before in past executions, you're going to keep this test case for further mutation, hoping that down the line it's going to reveal eventually some failure. And the most popular form of coverage as a feedback function is edge coverage, which means we track which basic blocks are executed in a program. Even better, we track transitions between basic blocks. So you get a little bit of path sensitivity in your exploration, and you build an identifier for the current basic block and the basic block that lead you there, and you use this identifier to update a coverage map, which tracks the overall coverage for this execution. Now, a few years ago, an influential paper, the Angora paper, proposed to extend edge coverage with context sensitivity in order to have more pervasive exploration. Now, the idea is that edge coverage is a local feedback. It's about a specific function, but doesn't track how you reached that function. And context can be represented, for example, as the calling context, so the sequence of function calls that brought you there. So what you can do is you can turn edge coverage into a context-sensitive feedback by taking, for example, the hash of the call stack, and you combine it with the edge identifier, and you use that to update your coverage map. Why would you do that, though? I mean, the advantage of adding context sensitivity, which you have also in other program analysis scenarios, is that in the case of fuzzing, there is some code which can reveal a problem of failure only if it's reached from certain execution paths, or if it depends on some program state condition, some global state, which might be set only across some execution paths. The problem with edge coverage is that it's local, so you might miss that information depending on what you did until now. So if the path that you need to traverse to reach the bug, you have reached it in other executions, so like your current coverage is a superset of what you need to expose this bug, then you're going to miss this bug. Or at least it's going to take a lot longer for your fuzzer to expose it. So we studied this problem, and we found that there are two challenges to context-sensitive fuzzing. There are efficiency challenges. We call them coverage map explosion and queue explosion. The first relates on how you track this coverage. So you maintain a coverage map, and this coverage map has a number of entries that is fixed. The moment that you add context sensitivity, your number of potential edges that you traverse becomes a lot bigger, and this brings collisions in your map. Collisions are bad. We know that already for edge coverage, collisions are bad. So what you can do is I'm going to use a bigger map, and that's what they did in prior research. The problem with that is that your performance is going to go down because every test case is going to take longer to be analyzed and compare and stuff. On top of that, you also have a problem for the fact that this feedback is very fine-grained. So you're going to keep a lot of test cases in your queue, way more than before. And it's not certain whether all these test cases are useful or if most of them are just very similar to test cases that you already had with edge coverage, but you're not sure whether, you're going to need this extra sensitivity or not. But at the end of the day, you obtain an exploration that is slower. You observe performance drops, and yes, you can find some bugs that edge coverage will miss, but your efficiency is not going to be so great. So we try to work on that. We say, okay, can we make this more efficient? What do we need to fix or to try from other angles? First, we wanted to get rid of the collision problem, and we came up with a design that is fuzzer friendly for encoding the context without collisions. And then we proposed to not apply context sensitivity everywhere, but to do it only on some program portions. And then the question is, which program portions? But I'm going to get there in a minute. Let's start with removing the collisions. So if you're doing normal edge coverage, traditional, instead of building hashes, which is the classic AFL way to go to track edges, what you can do is you can transform the control flow graph to obtain edge coverage from block coverage. How? So in graphs, you have something called critical edges, which are edges that are not the only edge leaving their source, and they're not the only edge reaching their destination, like the one in red here. But if you split these edges, you introduce some blocks, then what you have is that you can infer which edges you traversed just from the basic block where you're at now. So if you instrument basic blocks and you add identifiers for basic blocks, then you have an accurate edge encoding without collisions. And this is what they do now. They call it PC guard in AFL++, and this gives you very good performance for edge coverage. Now, we wanted to have this also with context, and we came up with this idea of cloning functions. So let's take this example here. We have function 4, which is reachable through two contexts. One goes through function 2, the other through function 3. And what we do is we create a copy of function 4, and we make sure that function 2 continues to call the original function, and function 3 calls the copy. Now, function 4 and the clone will have distinct edge identifiers, but they also carry some implicit context information because there is only one path that you can use to reach those functions. So you combine this with collision-free edge coverage, and you have an implicit context-sensitive feedback. And let's say that we have a solution for the first problem, but we still have the problem that there is too many paths, and this feedback is very fine-grained. Calling context, this is a well-known fact that they are really, really many. Sometimes they are exponential in the size of the core graph, and you have a lot of edges in code. So if you combine these two elements, you still have a very, very large space. We propose to do it selectively. So we decide that we can try to have selectivity within a budget. This budget is set by the map size because it's a main driver for performance, and so you can say, okay, I'm going to allow to have this many edges at most, and then you start cloning. How you do pick which functions you want to clone? We looked at program analysis literature for forms of partial context sensitivity, and we tried some strategies that are driven by the topology of the graph. So I can start, for example, from the root, from the harness of the fuzzer, of the program being fuzzed, and you do in a top-down fashion, or you do bottom-up from the leaves. You can try several of these alternatives. We saw that the performance was decent, was even better sometimes than context sensitivity, traditional context sensitivity, but edge coverage was still better. So we needed a different angle for that. We decided to reason on the data flow. So our reasoning was this. Fuzzers are really good at finding memory-related bugs. And memory bugs, we make this assumption that when the data flow of a program changes, then there might be, it might be more likely that you might have a bug there. And to study the data flow, we focus on the arguments that are being passed from one function to another. We focus on call sites, so on pairs of function. More precisely, let me use an example for this. Here we have function 5, which is reachable from 3 callers, okay, function 2, 3, and 4. And let's say that this function has one argument. So we study the potential values of this argument that are coming from the different colors. And we see that, for example, from function 2 and 3, you pass similar objects, while from function 4, you pass something that you don't see in this other context. That's a diversity. And we speculate that this diversity could be good for the fuzzer to track some helpful data flow diversity that down the line maybe will help for some bug. So we introduce a clone here. And there are two important remarks here to do. If I only go back, yes. The first is that we no longer need to study entire calling context, the entire call stack, but we can work locally, only for pairs of function. And the other is that, at least for now, we focus on pointer type arguments, because you're sure that if a pointer changes, the object changes and the data flow changes, while non-pointer arguments might need different reasoning, because you're not sure that you're going to have a data flow variation if some integer variable changes. But with the pointer, you do. So we combine these elements, and we build something on top of FL++ and LLVM, and we have source-based instrumentation, and we use SVF for pointer analysis. We have an Anderson-style pointer analysis, and the code is available. And we put everything together and we test it on FuzzBench. What are our goals? This talk, this research is about improving bug finding capability in code that fuzzers can already reach. So we don't want to improve edge coverage. We want to see if we can find bugs that other solutions might have overlooked in code that they already can reach. And then we want to see what is the price that we pay for this hopefully improved bug finding capability. So we measure the overheads. These are the main points of our evaluation, and we consider three main fuzzers. We take edge coverage in the collision-free version, and we augment it with link time optimization, so to have a very performant baseline. Then we have the Angora-style context-sensitive fuzzing based on call stack hashes and our approach. We did, initially we saw, the first metric is how many bugs you find. The first interesting finding is that the edge coverage, which here we call LTO, was finding more bugs than context-sensitive fuzzing. And this is because of efficiency, because that one executes faster, has better throughput, and in general has less trashing effects on the performance of the fuzzer. So it was finding, in this case, 112 bugs, so 10 bugs more than context-sensitive fuzzing. We found more than both, 11% more than one, 22 more the other, but what I want to stress here is more than absolute counts. What I found interesting is that our bugs are different. So not only, yes, they are more, but they're also different. We find bugs that are missed by link time optimization. Edge coverage with link time optimization. We looked at these bugs, and we saw that some, 2/3 of them came indeed from a better exploitation of the code. We were actually exploring program state more pervasively and getting the program into the right state to showcase the bug. But in other cases, we found a new coverage. And the reason is that by keeping this extra test case, the fuzzer was able somehow to meet some branch conditions which enabled new coverage, and this new coverage exposed new bugs. So this was a surprise also for us, because we didn't want to optimize for better edge coverage, but in some cases we got that too. We further checked these bugs because FuzzBench, at least in the versions that we test, had old releases of software that were 2 to 4 years old, and we saw how many of these crashing test cases were still real bugs, like in current versions. And we found that, quite a few were bugs, and 8 of them were security issues. We reported them, we got a number of CVs assigned, and we did all the responsible disclosure process. As for efficiency, we measured, for example, the first metric we wanted to see if we had actually queue explosion. And in our case, we measured an increase in the queue size of about 26%, which is a lot less than than the state of the art. And the throughput, the fuzzing throughput, is affected by the percentage that the slowdown that we introduce, we find that it's acceptable. Maybe it can be further improved with optimizations. As for edge coverage, here I want to spend just a few words. Normally with context-sensitive fuzzing, you will get less edge coverage because you're just spending your time in exploring in more depth some code, at least on short runs, in 24 hours. We saw instead that our fuzzer was doing really close to the baseline, and in some cases even slightly better. So this was good. This was confirming that in the end we're not introducing that much fuzzing overhead. And to build our binaries, this is a one-time effort. You introduce these clonings, and this is going to add a few minutes to your compilation time. You do it once, and then you start your fuzzing campaign. At the end of this journey, our research confirmed our initial intuition that if you want to do context sensitivity everywhere, like best effort on all the edges, you're going to face a difficult trade-off. It's either you're going to have collisions, and you have collisions, but you get good fuzzing performance and throughput, but you don't find many bugs, or you need bigger maps, but you kill your performance. So this is a difficult needle to thread. So we tried instead a different angle. We applied selectively, and we propose one embodiment to predict where this selectivity might be good. There is more work to do. We would like to study other prioritization policies. And another interesting aspect, which I don't have enough time to discuss, but I believe that this cloning technique might be helpful for other problems that we have in our community. For example, when we have to analyze indirect calls. So this is something that we are actually looking at. But that will be all for now. I'm happy to take questions, and thank you for your attention.
Okay, thank you for the presentation. I guess we have time for maybe one or two questions.
Hey, hi, Lucas from Santa Barbara again. Thanks for the talk. Quick question, can you elaborate a little bit on your pointer differentiation, when you think two pointers are different enough that they warrant cloning the function, and like what the intuition there is?
I couldn't get, can I elaborate, Tom?
On the pointer differentiation, where you pick when to clone a function, can you elaborate a little bit on the intuition?
Yeah. So what we do is we study, with pointer analysis, you can study abstract objects, right? So we study all the abstract objects that can reach a function, and then we measure in how many colors this object occurs. So we use that to obtain a priority number, and we clone with we give a very high cloning priority to those objects that appear at very few call sites compared to all the call sites that you have for that function. Also in the bugs that we found, usually the cloning priority was high in those contexts.
I see. Okay, thank you.
Thanks, good question.
Manuel.
Hey, Manuel Egele, Boston University. Thank you very much. Awesome talk. I particularly loved when you explained the types of bugs that you found, where you said we didn't only find more, but we found different bugs. So I completely agree, that's super cool. At the same time, you're also missing roughly 20% of the bugs there. So in your opinion, should we be forcing to find new types of bugs, or make sure that we, improve on the things that we have, that we don't have this missing 20%?
That's a cool question. Thanks, Manuel. On some level, there's some research that says that we should ensemble fuzzers because they are all good at finding different bugs. On the other hand, one thing that we didn't try was to run this for longer, let's say on 48 hours, because our fuzzer still has the same sensitivity of edge coverage. So it's not like we are giving up on those, but in the buffer, in the time that we have, we just couldn't reach those bugs. But yeah, that will be a great follow-up work for this. Thanks.
Okay, we have another question.
Hi, Apik Roy Choudhury from NUS. Thanks very much for your very clear presentation. So the data flow oriented fuzzing has never taken off because of various reasons, and you kind of provided a situation where it works very well, essentially cloning these functions based on the data flows. So I wonder whether you have also tried this idea in some limited way for the intra-procedural fuzzing, because you see that's where it gets complicated. Trying to clone the basic blocks, you can't do that all the time. So what are the strategies? So I'm just curious whether you have tried it out and what were your experiences, or even some comments. And also thanks very much for the work.
Thank you so much. That's actually we are doing something on intra-procedural paths, and one of the ideas that we had on the table was cloning. But for intra-procedural paths, there is also an old algorithm for enumerating them. It's the Bollarus algorithm. So actually, we have an ongoing project where we are trying to do that. The problem with why we chose this technique over cloning, because at the intra-procedural level, then it's possible that you have to fight with the compiler optimizer that might merge against stuff. So either we should intervene really down in the compilation pipeline, but then you might have other issues like you're instrumenting some locations multiple times where you don't really need. So it's more for an engineering reason that we haven't tried cloning on intra-proceed to, let's say, expand paths. But that's a very interesting question. I'd be happy to chat after on this if you like.
Okay, thank you, Daniele, for the presentation.
Thank you.